At this point, we've looked at what happens to a gas when it's by itself. If I have this one gas at this temperature and pressure and volume, how many moles would there be? Or if I take this one gas and I cool it down at constant volume and constant pressure, what would happen to the moles? Those kinds of things we've looked at. But the truth is that everything gas-like often happens in mixtures. And so we need to talk about what happens when there's one or more gases in the same place. And the good thing for you is that it's actually a pretty simple principle, right? The name of this particular principle is called Dalton's law of partial pressures. And it just says that if there's a mixture of however many components, right, A, B, C, are just the components in the mixture, the total pressure, right, and so sometimes you'll see instead of P mix, P total. It's just the sum of all of the pressures. Conceptually, underneath what that's saying is that one gas is the same as another. It doesn't matter if I have a container with a certain number of gas particles that are all the same, or if I have a container that contains several different gases, right? I'm just using different colors. The fact is that according to ideal gases, right, all chemicals are the same. It doesn't matter whether it's a mixture or one. The total pressure, right, P total, is proportional to the number of particles, which we count by moles. And so there's simple ways to do this and more complicated, and we'll look at a few of those examples. First off, if I've got a gas mixture of three things, right, so this is one component, this is another component, and this is a third component. If I use Dalton's law, I should just be adding them up, right? P of the mixture should just be 0.182 atmosphere plus 0.195 atmosphere plus, now here's where the problem is, right? I certainly can't add atmosphere, atmosphere, and millimeters of mercury, right? That's the only trick to Dalton's law. All the units have to be the same. So I better convert this, right? I divide by 760 millimeters of mercury in a torr. So really the total pressure is 0.182 atmosphere plus 0.195 atmosphere plus 0.095 atmosphere. And if I add all those together, I get a total pressure of 0.472 atmosphere. Right? Dalton's law is as simple as identifying the components, making sure all the pressure units match, and adding them up. And so what typically happens with Dalton's law is we give you more interesting problems than this. So let's look at one. So here's a can of compressed air. And I see as I scan this problem, again, three components. It doesn't have to be three components in a mixture. It just happens to be in this case. But I'm not given any pressures this time, right? I'm given grams of the three gases. It looks like I'm given the volume and the temperature. Okay, that's a little bit different, right? I have to find the pressure of each of these components. And here's what I want you to recognize. We know the ideal gas law, don't we, right? PV equals nRT. If I want pressure, but I'm given volume and temperature, and grams can certainly go to moles, I have everything I need to find my three pressures. So go ahead, and again, according to the way ideal gases work in kinetic molecular theory, one gas is the same as the other. I can do a PV equals nRT on nitrogen, a PV equals nRT on oxygen, and a PV equals nRT on carbon dioxide. Let's see what happens. Pause it and give it a try. So here we are, right? I used grams to go to moles, so just regular old stoichiometry. And then once I had moles, I put it into the ideal gas law. You notice that for all of the gases, the temperature is the same, right? It's not like there's one temperature for oxygen and one temperature for nitrogen and one temperature for CO2 in that can of gas. It's all the same across. Similarly, the volume is all the same. The only thing that changed is the moles that I put in based off of the grams. So I have my 3 separate pressures. And so now my total pressure is just to add them up, right? So the mixture in the can is a pretty high pressure, isn't it? And that makes sense, right? This is a can of compressed air, like the kind you'd spray on your computer keyboard to clean it out or something like that. So it's very pressurized in there. Oops, sorry, plus 19.9 atmosphere. So overall then, 154 plus 46.3 plus 19.9 is 220.2 atmosphere. Super high pressure in there, and that's okay, right? Again, this is a can of really, really compressed air, so it's going to be a lot more than atmospheric pressure. Let's try one more example of Dalton's law. And as I scan this problem, I see 2 components, neon and CO2. And I see that they're added sequentially, but that doesn't matter to the final state, right? By the end of this, I have a mix of neon and CO2 in a 3-liter container, right? Because the container didn't change size. And the other thing that I know is 27 degrees Celsius. We're trying to now figure out the partial pressures of the 2 things and then the total pressure. So let's see what we can figure out. Take a moment and see if you can use any of the strategies in our previous problems to start figuring out how much neon or how much CO2 and then the partial pressures. So after perusing this problem, I hope you found that the way that this problem is written, the neon was in the container at the beginning, right? So this 770 millimeters of Hg is just the pressure of neon. So I can just use that number and say, that's the partial pressure of neon. And I want to convert it to atmosphere, so I have it for later. As far as the CO2, that's a little bit more complicated, right? But we've done this before. They gave us some grams. They gave us a volume. They gave us 27 degrees Celsius. And so we can go ahead and solve for the pressure. We know the moles, we know the liters, we know the temperature. And we can find that the CO2 has a pressure of 0.115. And so after that, it's all over but the math. We add the 2 things together. Oops, sorry, plus 0.1, and we'll just make it 12 atmospheres. So the total pressure equals 1.13 atmospheres. Mixtures are just about separating out the components, identifying things in the problem that will let you find their pressures, and then adding them together to get the partial pressures at the end.